This is
STEM Z Perspectives.
Hello and welcome everyone to another episode of STEM Z Perspectives, a podcast by the Young Scientist Journal. I'm Harry and I'll be one of your hosts for today. My interests are in engineering, computer science and earth sciences as well.
Hi everyone, I'm Stella. I'll also be hosting today and my interests are in aviation, astronomy and physics. We're super excited for this episode today.
In today's episode, we're going to be joined by Dr. Alex Kontorovich, Professor of Mathematics at Rutgers University in New Jersey.
He'll be telling us a bit about his day-to-day work and what being a mathematician involves. Oftentimes, the work the mathematicians do may appear very abstract, so it's important to bridge the gap between mathematicians and the public. And now let's turn to our guest, Dr. Kontorovich. Hello, nice having you here.
Thanks for having me. Pleasure to be here.
Yeah, how are you? I know it's tough times for us all, so how are you? How have you been coping with lockdowns and that sort of thing?
Yeah, just making do, one day at a time.
So the usual. I'm sure everybody else in our audience is probably doing the same thing. So as you know, this episode is on what mathematicians work on. And to start us off, could you tell us about the various roles you have and what your day-to-day life as a mathematician looks like?
Sure. Well, right now my day-to-day life is a little different from usual. Usually, I'm either just sitting around doing research all day, or I'll have meetings with my graduate students, my postdocs, my collaborators all over the world. That's actually been one nice thing of this, if you can call it a nice thing, of the pandemic, is that people are now much more comfortable and have lots more tools to collaborate virtually that we didn't have before. And there's kind of no reason that we didn't use them before. They were around. It wasn't the standard. We could meet, I'll see you in Japan next month, or I'll see you in Germany in a week or whatever. We saw each other sufficiently frequently, even though we were scattered all over the world, that we didn't need the tools. Now I need the tools just to talk to my own colleagues in my department. And so it makes it just as easy to collaborate with Moscow as it does to collaborate with, New York City, 10 minutes away. So that's the bulk of my time is usually spent on research in one form or another. Of course, there's also a bit of teaching thrown in there. I'm on sabbatical as we speak, so I'm not teaching a course right now. In lieu of that, I'm the visiting professor at the National Museum of Mathematics in New York, and so I'm giving a course to the general public.
On your website, it says your interests are analytical number theory, harmonic analysis, automorphic forms, representations and L functions, hyperbolic geometry and spectral theory, group actions and ergodic theory, and sieve and circle methods. Could you tell us a bit more about some of these topics and whether they can be connected to anything in high school mathematics or science?
Oh, that's a good question. I guess, let's see, there was a long list of things that you said. Well, I guess it's my fault for putting them there in the first place. Right. So yeah. broadly, my research is in number theory. So number theory enjoys, if you like, this position. Well, at least the famous Carl Friedrich Gauss, I think once said that mathematics is the queen of the sciences and number theory is the queen of mathematics. So number theory is one of the oldest subjects. It's basic questions about whole numbers. These are things we should be teaching to our kindergartners, not only our high schoolers. Well, what can I say? There are a lot of, it's a huge modern industry, and there are a lot of tools and techniques, and that's what some of the things that you said were the tools and techniques that go into solving basic questions about whole numbers. So one perhaps that your listeners may have heard about is something called Fermat's last theorem, So Pierre de Fermat was studying the Pythagorean formula, x squared plus y squared equals z squared. If x, y, and z are the three sides of a right triangle. And there are lots of integer solutions to that equation. Like 3 squared is 9, and 4 squared is 16, and 9 plus 16 is 25, if I've got that right, and 25 is 5 squared. So 3 squared plus 4 squared is 5 squared. So there are lots of integer solutions to that equation, and Fermat asked whether there are integer solutions to equations like a cubed plus b cubed equals c cubed, instead of a squared plus b squared equals c squared, or a to the fourth plus b to the fourth equals c to the fourth. Do any of those have solutions? And this was famously resolved by Andrew Wiles and work with of Wiles with Richard Taylor in the mid 1990s, which was a 350-year-old open problem, one of the crowning achievements of 20th century mathematics, and has absolutely no use in science or engineering. It's just a question that humanity struggled with and built amazing tools. The tools that went into the resolution of that problem are, I would say, much more important than the problem itself. But certainly it's nice to have that cherry on top to be able to have a statement like this, that we can, it's a testament to humanity's ability to work in groups. There were, the breakthroughs were by individual mathematicians, but they're all building on work of their predecessors and the community at large coming together to solve this problem. So it was just a fantastic breakthrough.
You hear this so often, that maths is just all about problems, and it's so obvious. Trying to come up with all these equations and how they interconnect and how they match up with each other. It's really interesting and a really fascinating topic. So on to our next question, which is, what are you going to be, or what are you researching at the moment?
Yeah, that's another very good question, and one that's not so easy to answer, especially in a podcast format. But well, there are a number of ongoing projects. One is about the study of something called manifolds, and manifolds are just generalizations of things we're used to looking at, like donuts and pretzels and things like this. Like if you imagine the surface of a pretzel, it's rather complicated. It has all these holes and places that you can go around. And there's a wonderful video of someone driving a motorcycle. Imagine being an ant on a motorcycle on the surface of a pretzel, and but you can't steer at all. All you can do is go straight. So you're an ant, and you just start circling around this pretzel in bizarre ways. And it turns out that there are lots of these, what we call geodesics, which is just moving in a straight line, except the space is curved. The space on which you live is curved, like the surface of a pretzel. And you go around this pretzel, and you come back exactly to where you started. So that would be called a closed loop. And people study these loops, and there are connections between, surprisingly perhaps, these loops and basic number theoretic questions that people like to understand. So things like the distribution of these loops, and where do we have lots of them, or do we not? Do they cluster together? Are they well separated? Things like this. So that's sort of a dynamical question involving topology, geometry, differential equations, and dynamics, ergodic theory, things like this.
Wow, that's really so cool. That's so cool. Was there a certain moment where you decided to become a mathematician, or was it more of a process?
Yeah, that's a good question. So for me personally, I was born in Russia and came to the US when I was in 3rd grade. And so I didn't speak the language, a word of English, and I didn't understand any, I just sort of showed up in school, and they put me in these classes with these weird letters that I didn't know and saying weird things. And then they stuck a math sheet in front of me. And this is stuff I'd seen years ago in Russia. So somehow the Russian system is a little bit ahead of the American one. So it was just it was the class that I looked forward to in school because it was the only one that I could actually do anything in for the first while. It didn't hurt, to be fair, that my mother is a mathematician. And so I also got a lot of that at home. But I never thought that I would go into research mathematics because I didn't know that research mathematics was something people really did. Maybe you get a PhD and then you go into business, or you go into finance, or you go into something. But so that's kind of, I think, what I had in mind when I was an undergrad. Even when I started grad school, I think I half thought I would finish grad school and work in industry. And I was very fortunate that the problems that I found and was given in graduate school, they were, first of all, ones that fascinated me to the point that I didn't want to let them go. I just, you wake up in the morning and the first thing you want to do is start attacking them. And there are lots of problems like that, like the famous Riemann hypothesis, which maybe your listeners have heard of, that you basically can't make any progress. No one has ever made progress, serious progress, on these problems that have been around for hundreds of years. So you have to get lucky and find something that you find really interesting and fascinating, and where there are tools where you can make concrete progress in a period of, a PhD is only 5 years. And at the end of that time, you need to have something so that you can get a postdoc. And after a postdoc, you need to have something else so you can get a tenure track job. And then you need something. So there's this sort of ever progressing tower. And I guess by the time you reach my age, I mean, I have more problems than I know what to do with, which is where my graduate students come in and postdocs and so on. So yeah, there's a funny thing, you can say, where do problems come from? Well, where does music come from? Someone just makes it up and it sounds good and it sounds interesting and people decide to play it. And same thing with problems. People decide to play with interesting problems that people come up with. Some people are better at coming up with new problems. Some people are better at solving problems that others have come up with. So there's just a whole world of mathematics inside the research mathematics community that I think very few people are exposed to, but that's part of what we're doing here. So I think that's what drew me in eventually, was the problems.
It's so interesting. Obviously, coming from another country, and math sort of being this common ground, if you will, that everybody knew about it. You could see it as a universal language, that is accessible to everyone. And the fact that you came across it and you found out about it, as being your subject that you liked so early on. Was this the point where you first saw yourself as a mathematician, or did you think, oh, I'd rather follow another career path?
I think so. Certainly, when I was finishing college, I did not know that I would continue in research mathematics. But by the time I was finishing my PhD, I knew that that's what I wanted to do, and that's I've been blessed and fortunate and privileged to never work a day in my life.
So you're an editor-in-chief of the Experimental Mathematics Journal. How exactly would you define the field of experimental mathematics, and what exactly does it involve?
Yeah, that's a great question. It's a very difficult one for mathematicians to answer. It's constantly something that we discuss with various board members and the referees and so on of the papers that are submitted. I think of the Journal of Experimental Mathematics as some place where we're not ready. The mathematics is not yet ready for the problems that are being submitted there, but there's definitely something to the problem. It's connected to something, but the people who have discovered some nuance, some interesting new phenomenon, don't even know who to talk to try to make progress on it. So there are established journals in topology and geometry and algebra and number theory in all these different fields, in knot theory and differential equations, where people understand these are the types of problems that we like to solve. These are the types of tools that we like to use to solve those problems. We can develop new tools. We can develop, variations on existing problems and so on. Experimental mathematics is much more broad than that. It's I don't know where this problem belongs, but it's absolutely interesting and connected to other things. We just don't know what, and we don't know what. We don't have the tools to say what's connected to what. So my kind of ideal paper in experimental mathematics is one that at the moment nobody has any idea what this new data, and data, by the way, does not mean computer experiments, or certainly not physical experiments. It can mean some little lemma, something someone's proved rigorously, but it seems like it should be connected to much more general and broad things. So something, as I said, the ideal paper for me is something that maybe 10 or 15 years, 20 years later, that main idea or that main conjecture has been resolved and is a paper in the Annals of Mathematics or in the Journal of the American Mathematical Society, one of the top journals. So it's a paper where if you could actually solve the problem, it would be a paper in a top journal. And well, we don't know what the tools are that will eventually go into the solution. So then I wanted an experimental mathematics.
So literally experimental. So obviously we've heard of applied maths. I'm sure many of our listeners, particularly in the UK, know that applied maths is very much a thing. But what can experimental maths in particular be applied to? What further things can it contribute or go towards?
Yeah, so experimental math, even though it sounds like it's something applied, it's only applied in the sense that it is applied to other pure math. At least the way that of course, there's other kinds of experimental mathematics that does go towards applied math, but I'm a pure mathematician. And so some of the best mathematics has come from people sort of breaking rules. So if you think about all these things we learn in school, first you learn whole numbers, 1, 2, 3, 4, 5, and maybe you learn to add them, maybe learn to subtract them. And then at some point somebody says, what's 6 minus 8? Well, that's breaking it. You can't take 8 away from 6. There's not enough. And so you invent these new numbers, these negative numbers, and you experiment. What happens if we invent these negative numbers, and how do we deal with negative numbers? And then you learn about multiplication, you learn about division, and then someone says, what's 9 divided by 7? You go, wait a second, that's not a whole number. I need a whole new concept of rational number, of fractions, to deal with this. And then, well, once you introduce that idea, now you have to figure out how to add fractions, how to multiply and divide them. Eventually someone starts squaring numbers, and then you say, well, what's the square root of 4? Well, it's 2, but by the way, -2 is also, if you square -2, you also get 4. And then somebody says, well, what about the square root of -1? Is that a thing? And but wait, the square of any number is positive. So how could you try to take the square root of a negative number? And then you get into complex numbers, imaginary, what we call imaginary pretend numbers. So math is regularly broken. And when math breaks, that's when you're about to learn something. It's the same in science too. It's not the experiments that confirm previous knowledge and previous models that are the groundbreaking ones. It's the ones that show failures, show discrepancies. Newtonian mechanics worked perfectly well until people could compute things to such a high precision that there was deviation, but a regular deviation, not just some random deviation, but consistent deviation from the model, until Einstein's general theory of relativity could be worked out. And now we have, we experimentally observe, we haven't broken Einstein's theory of relativity yet. Well, at least on certain scales. So it's similar in math. Math is constantly broken by new ideas that challenge where previous ideas worked. And so that's the goal of experimental mathematics, is to bring these new kinds of ideas. It's not necessarily that it's going to go towards applied math or towards science or towards helping humanity. Unfortunately, that's not our business. Although I will say that every society that invests significantly in these kinds of pure thought experiments and allows freedom for people to just explore wherever they get to, eventually that society reaps great benefits, sometimes decades or centuries later. So just like negative numbers, negative square roots of negative numbers, imaginary numbers, were these pretend things that were just useless mathematics that people played with for fun. Centuries later, it was very much needed in development of quantum mechanics, for example. And same thing with general relativity. People were worried about non-Euclidean geometries for very pure mathematics reasons. They were not thinking about anything related to the real world. They wanted to prove the parallel postulate or some, I mean, we can talk about that maybe another time. But they were basic questions being asked for really no reason other than human curiosity. And if you allow that human curiosity to flourish over decades, centuries, and millennia, if need be, who knows where it will lead us. So in the case of these questions about Euclidean geometry, it led us all the way to the mathematics being in place for Einstein's general theory of relativity to be, he could plug into an existing mathematical theory that previously only existed because we thought it was fun to play in 17-dimensional curved space.
I'm pretty sure most of our listeners are really loving the fact that we have explored in experimental mathematics, but I'm also certain there must be those who are quite curious about what exactly do you do as an editor-in-chief. So could you try to tell us about what that is? Yeah.
Sure. Well, that process really isn't all that difficult. There's the main job is to kind of have a nose for who are the experts in fields that don't exist. That's really the most difficult part of the job. When a paper comes in, and these are not, again, if I'm in algebra and number theory or geometry and topology, I have my group of people who the papers will have a certain flavor of problem. They'll have a certain flavor of tools that are being used in the solution. And I know who the world experts are in these things, and I can just send it to them and they'll look at it and they'll tell me, they'll referee it. You know, mathematics papers and science papers in general go through refereeing processes to make sure that everything, well, to do as best we can to make sure that things are correct and proved rigorously when there is a rigorous proof to help with the exposition and things like this. So really the hardest thing about being the editor-in-chief of experimental mathematics is that papers come from left field and from fields that don't exist. So sometimes I have to go to 15 world experts before one of them says, wait, this kind of smells like something I could tell you something about. And then we have a conversation, we sort of discuss the merits of the paper and whether it can be accepted or not. You know, unfortunately, I mean, we receive something like, I don't know, 250 submissions a year, and we can publish only maybe 20 papers. So it's a very competitive journal. We're blessed to have lots and lots of top contributions coming in. So yeah, so the hardest part of the job is, you know, finding which of these papers. It's sort of being a soothsayer, right? I have to read the palms and read the tea leaves and figure out which of these papers that at the moment you don't know where they're going, if anywhere, which of them will, if invested in, will sprout roots and turn into a full-fledged subject eventually.
I mean, even at the Young Scientist Journal, we get we have our own senior team, and we get just so many articles being submitted. I think we get 2 or 3 from young people every single day. So we're getting so many, and it's really good to have those experts that are experts in their subject area that are able to find the best people, find the best information, find the best original research. And it's really interesting to see what the youth come up with. As well as being editor-in-chief for that magazine, that journal, you're also a scientific board member at the Quantum magazine. So What work do you do there? Do you provide support to science journalists regarding technical information?
A little bit. There are certainly times when journalists will contact me and say, you know, can you give me some, more often than not, it's not that I'm giving them direct content, it's that I'm sort of pointing them to people who can help. Certainly when I hear of interesting new things that we should be covering, I bring it to the attention of our writers and editors. Mainly I'm consulting there, you know. So I'm not doing, with one exception, I'm not writing anything directly for them, and I just try to be their eyes and ears in the math community and point them to things that I think they might enjoy covering.
So as someone within the mathematics society, as a mathematician yourself, what do you think are some steps that those who are within this, that are working within STEM can take to communicate science and mathematics more effectively, like towards the people, towards like basically their like communities around them?
Yeah, that's a really hard question. You guys you got great questions. You've done your homework for sure. It's hard. I really don't know what to say. I genuinely don't, because every time that I've seen sort of some big push in, I mean, there's a crisis. There's absolutely no question that there's a crisis in the way mathematics is taught in schools. I don't know about around the world, but certainly in the US, that it's something that people are, it makes them afraid of mathematics. It makes them, I don't know I don't have the numbers on what fractions of people are actually proficient at grade level, whatever that means. But it's a crisis, and every time someone steps in to fix it, it only gets worse. So I'm going to try to take the Hippocratic Oath here and do no harm, first and foremost. I really think that, well, one of the programs I'm trying to bring to the work with MoMath, the National Museum of Mathematics, is outreach to parents specifically, because parents, unlike teachers who have to conform to standard curriculum that's being given from someone else, or principals or book writers, you know, textbook writers and so on, parents, there's no barrier. If a parent learns some cool piece of mathematics, they can go to their child and just play. And this is personally how I learned mathematics, because my mom, again, is a mathematician. So for me, every car ride, you know, if we had some long car ride to go skiing, you know, 4 hours away, then that was 4 hours of my mom just giving me problems to do in the car. And there were always some fun game. It was never like, here's a worksheet with 1,000 long division problems or something like that. Not that that's not a necessary component of math education. You know, there's just like if you want to play, I mean, it's kind of amazing, because if you look at sports, you know, we produce these incredible basketball players, and everybody knows that if you want to be a good basketball player, you have to go to basketball camp, you have to have the top trainers. You see these kids, I don't know about in your high schools. I remember in high school, there were kids that just had a ball and they dribbled the ball every single place where they went. They went to have lunch, they were dribbling a basketball. They went to on the bus, they're dribbling a basketball. Like if that's what you want to do and that's who you want to become, there's a very clear thing to do, which is not just have fun and play games, but dribble the basketball. So same with math. We need to have, I think we have, it's almost too much of both sides. That people try to make math fun in ways that aren't actually fun for kids, and they try to make them do the hard work of dribbling, if you will, drilling things without people actually learning the skill. So I don't know if I answered your question, but somehow
you definitely have. I totally understand and get the perspective that you're coming from, because in the world today, honestly, most students, like speaking as a high school student who is offering mathematics, the way that the material is delivered to us is not in such a way that's like it's making it interesting, unless you've had the interest right from the point when you're like young or like in primary and you're growing with your love for mathematics. But if you're just like starting out and you're just like, oh, I'm just learning this to get a degree, get a career, there is no purpose in life. The way they deliver the content, it doesn't give you the purpose. So I totally understand, and I hope our audience is also getting something from this.
Yeah, but unfortunately I don't have any solutions. I mean, I have lots of utopian solutions, but that's the thing that happens when you bring utopian solutions to the real world. Every time, this has happened time and again, people come with new curricula and they say, okay, we just have to train the teachers. If we train the teachers, first of all, the teachers, they had math in a certain way and they've been teaching that math for 30 years. And now someone comes and says, teach it this completely other way. They get scared of it themselves. And of course they pass that fear onto their students. Secondly, the parents have no training at all. And the child comes home and says, Mom, I don't understand this homework. Can you help me? And mom says, I don't know what to do.
I don't know what's going on.
Yeah. So that's why I say, first and foremost, do no harm, as I think plenty of harm has been done.
Yeah, true.
Finally, just to wrap up the interview, I know the clock's ticking down on the free Zoom, but have you got any piece of advice, short, sharp advice, or maybe a quote or a mantra that you go by, that's some sort of advice or advice to yourself that could be applied towards middle school or high school students wishing to pursue a career in mathematics?
Sure, that's very easy. As things get worse and worse in schools, we were just talking about, things get better and better outside of school. There's YouTube, which was not around when I was growing up. And now you can watch videos by 3 Blue 1 Brown and Vsauce and Mathvlogger and Veritasium. And there's these incredible channels that are providing content completely free. It's incredible content. It's full of energy. It's full of excitement. And so I would just not look to school for inspiration, but look elsewhere, because there's plenty of it and it's all out there. And the world is you're the future. The world is yours now.
Thank you so much. It's been really interesting. I'm sure we'd all love to spend more time.
It's been educating and awesome.
My pleasure. Thanks for having me.
Yeah.
It'd be great. Perhaps if you come back and speak, perhaps even in a few months' time about a more specialist topic, or perhaps I'm sure Hazal and other people on our team would love to have you at one of our events, perhaps at our conference.
One of his research topics, yeah.
Sure.
Thank you so much.
Thanks, Harry. Thanks, Stella.
Thank you so much, Dr. Kontorovich. Thank you. Nice meeting you.
Thank you. Nice to see you.
Take care.
And I'm sure as an audience, and particularly for Stella and I as hosts, we learnt a lot from this interview.
Yeah.
Oh, and there's so much that we can take away. Like, particularly in his eyes, parents are really a driving force into getting into mathematics. Schools have to teach so much. They have to give everyone a basic understanding, basic idea of the curriculum. But it's the stuff that you learn from outside, so YouTube, what parents can tell you, what they can help you with, is really a driving force, and it allows you to learn so much more. He also spoke about experimental mathematics being able to be linked so much, how it's interconnected, and there's so much of a correlation between experimental mathematics as well as science. And even he started from quite a humble beginning. He saw maths as being fun, as it being a subject that he understood as a universal language, having come from Russia at such a young age, and then coming to an American school. He didn't see it as a career path to start off with. Stella, have you got anything else you'd like to add?
I definitely have learned a lot from Dr. Kontorovich. especially when the advice that he gave to young adults like wishing to pursue a career in mathematics. And he said, so obviously the fact that we have all these resources around us and we just need to, tap into them. And he said something of how mathematics is all about, it's either about solving new problems or adding on to problems that were already solved. It's all about breaking down mathematics to like bring up new ideas, because like every time you keep on breaking down something, you just keep on multiplying and getting like a bigger bounty, a bigger outcome that's really wonderful and nice. And I really love the communication that he quite gave. It was very awesome and very educating. We hope you all enjoyed this episode. Thank you so much for tuning in with us.
You can learn more about the Young Scientist Journal on our website, ysjournal.com, as well as our social media handles, which will hopefully be found in the description. You can also support the podcast by going to buymeacoffee.com/wisejournal, where you'll find options to buy us a coffee, or perhaps donate slightly more and help support the podcast. It will help with our audio quality, so we're looking to get some new microphones for our regular speakers, such as Stella and I. And by buying a coffee, signing up to membership, or getting an extra, you'll also have a chance to suggest a guest which we may feature in our next episode. And we'll see you very soon for the next episode of Sensi Perspectives.
Bye bye.